Hey guys, this is the second video in my series of building an end-to-end machine learning pipeline. In the previous video, we train and monitor our model with PyTorch Lightning. In this video, we will be performing inference with the model we train and convert it to the ONNX format, which will be later used to create a Docker image. So first, let's load the train model and evaluate its performance. I will do this by creating a separate Jupyter notebook, which I name inference .ipynd. So this notebook is put at the root directory, like in this format. So in this notebook, we will load the pre-trained model, set up the trainer by calling the trainer from PyTorch Lightning, and then do the validation of the model on the validation data loader. So let me turn off the camera here and we go through the codes. So here we need to import the model, the data, import PyTorch Lightning, and we use Hydra to load the model configuration, and we use weight and bias logger in the integration into PyTorch Lightning when we train. So the model checkpoint path is here. We will, in this case, we will manually initialize Hydra and load the configurations. So here is a loading of the model. So we will load it from the checkpoint, where here is the checkpoint path. And we need to specify, for the model structures, we need to specify the layers, which is simply the backbone of VG16. The in channel is, in this case, equal to 1. The number of classes is the number of emotion classes, and we can get other hyperparameter from the configurations. So here we just print out a message saying that the model is loaded, and we print out the total number of parameters for the model. And then we set up the trainer. In this trainer, we need to specify the weight and bias logger that we use for training. So this is the weight and bias logger I use for the training. So to set up the trainer, we simply go PyTorch Lightning trainer with this specified logger. And then we need to load the data. So we need to set up the data by first loading it and then set the data state to fit. So this command will initialize the data set and split it into the training data and the validation data. So here, because we want to validate the model performance, we only need the validation data loader. Now let me run this command and see the result. Well, it looks like I didn't put the data file in, so let me just put it in here. So this is the file that we use to process the data. Let's run this again. Okay, I guess I need to restart. Alright, so now I'm missing this CSV data file. Because in the data loader we call the CSV file, so we need it. Right, so now you can see the model is loaded and we have 14.7 million parameters. It could take some time to set the data, to set up the data. So let's see what is the performance on the validation data. Okay, so the data is loaded, and now we're doing the validation step. So here note that in the validation step, each of the original image, which has size 48 by 48, will be cropped into 10 sub-image, each with size 44 by 44. We make prediction on the 10 sub-image, and then we average our prediction. So here we can see that the result is the accuracy for the validation dataset is about 70.4%. Alright, so next we are going to use this train model to do inference on image, on video, and on the live webcam. In order to do this, I will create a file called inference.py, a Python file that is put at the root directory. So here, let's go through the details of this file. Basically, when we want to do inference on an image, there will be two main steps. First, given an image, we need to extract the facial regions of the image. And secondly, we will use our model to classify the emotion from the extracted facial regions. So here, let's look at the import, or the usual import. Here, I use the API face recognition in order to extract the facial regions in an image. And then it is just all the other imports that we already see before. So here, to do the inference, I will write an inference class. So in the init method, here is a list of 7 emotions that we use for this problem. So I give a dictionary where the keys are the integer from 0 to 6. The values here are the emotions. So the value here is a list of emotions, color of the bounding box for the emotion, and then color of the text, which is used to write the emotions. And then we load the model. So first we load the configurations, and then we initialize the model by loading it from the checkpoint. Okay, so here, in order to load the model, we need to specify the model path. And we will put the model to evaluation mode. Here in this case, we are doing inference, so we will put it in evaluation mode. We move it to CPU. Here I'm using a Mac. If you have access to CUDA, I'm sure that it could run way faster with CUDA support. And here is the transformation that we use for inference. So if we are given any facial region, we will crop that facial region into 10 sub-image of size 44 by 44, and then we stack them. Right? So this is the transformation for inference. And here is the code for inference image, inference video, and inference on a live webcam. So basically, again, we do 2 steps. First, we use face recognition API in order to extract the facial regions. And secondly, we use our model to classify the emotion from those facial regions. The most important function in this class will be the function where we give prediction on a certain facial regions. So this function is put at the end. So we will predict the emotions on facial regions. So here, the input is the facial region image. So the first step will be to convert it to grayscale and then resize to size 48 by 48. Note that our data, original data, has all image with size 48 by 48. So the first 2 lines here, we convert the given image to grayscale and resize to 48 by 48. Next, we will apply the transform on the image. So transformation here simply crop the image into 10 sub-image and then stack them together. Well, at this step, the image has shape 1 by 48 by 48. And after we crop it into 10 sub-image and stack them together, we get a tensor with shape 10 by 1 by 44 by 44. So now we get the prediction by running the forward method on the inputs. So because we have 7 classes, so each of these 10 sub-image give us 7 logits, right? So the output in this step is 10 by 7. The final prediction is the mean of all the prediction. So we simply take the mean here, and the final prediction is a list of 7 logits. So with this prediction function on a single facial regions, we can do all the inference. So here is the code for the inference on an image. So to do inference on an image, first we extract out all the location of the facial regions, and then we loop through all these locations, extract the face region, get the prediction, and then draw the rectangle and put the text on the facial region. For the inference of video, we pretty much do the same things, but for video we need to read the frames sequentially. So first we read the video, extract out the video feature. The feature we need is weight and height and FPS. Here I also extract out the number of frames, so I can print out the informations. And then we create video writer. So this is a video writer in the MP4 format, and here we loop through all the frames, right? And I use DQDM just simply to print out the process. And while the video is open, we will read the frame consecutively. A particular frame where we cannot read, print out the message that is failed to read the frame. And for the frame that we can read, now this single frame is simply an image, and we can do the inference on this frame as the inference on a single image, right? And then we will write the updated frame into the video writer, and we update the progress bar. At the end, we need to close the video and close the video writer. So this is inference on a video. Next is the inference on a webcam. So here, this function take in camera index as the parameter. If you only have one camera, which by default is your computer camera, this could be 0. If you have external cameras, then you might key in 1 or 2. So here we also start by opening the webcam, right, and loop through all the frame. The difference between this case and the case of inference video is we want to do it in real time and we want to do it fast. So here is a little trick in order to do this faster. So instead of doing prediction on the original frame, we are going to resize the original frame by factor 1/4. So we will make the size 4 times smaller so that we can speed up the prediction. So this is the small frame where we resize both the height and the width by 1/4. And then after that, we do exactly the same thing as before. So here we extract face locations and then loop through all the locations to give predictions. And here, one thing to note is once we already get the predictions, we will need to rescale the resize frame to the original size, right? So here we need to rescale the locations of the bounding box by multiplying everything by 4. So the top right and the bottom left coordinates all are multiplied by 4. And the final step here is to display the emotion and draw rectangle on the facial regions. And we want to show it live, so we use this cv2.imshow, and we want to set up a key so that we can close the video stream. So this is the way I often do. Whenever we hit the escape key, which is 27, we will break out of the video stream. Now it's time to see the result. First, let me open a new terminal, And here we want to run inference on image path, so we use this command. Let me extract an image from my local computer. So here I need to copy the relative path to this image. Let's hit enter and run. Well, now model is loaded, and here is the inference, right? So not too bad. There are a few cases where we don't have detections. For example, this case here. The reason is because the API face recognition failed to detect the face in this case. This case because a lady is turning away. This is because the hand blocked the face, and this is due to the mask. Overall, it looks reasonable, even though a few cases where, yeah, I guess happy is misclassified as angry. I think mainly because in the dataset, the angry emotion often comes with a person who show this. So whenever the model see a face with a lot of this, it will classify as angry. Okay, to escape this, you need to hit escape. So now let's see the inference on a video. So let me show you. Okay, let me just copy this command and paste in the path to the video. Well, this is a long one, right? It has almost 900 frames with high resolution, right? And here we are processing the video. It will take a while, so let me come back when this is finished. The process is finished. It takes about 300 seconds, which is 5 minutes to process this video. So now let's look at our result. So this is the result. Well, unfortunately we cannot open it directly. So here is just the video between Jack Ma and Elon Musk. I could have included the audio because I find this video funny. Well, I guess it's okay, not too bad. In general, the emotion prediction problem is a difficult problem because it really depends on certain facial features. Different people have different ways to express emotions, so it's not an easy problem. Right. For example, here you see Elon. Most of the time, his face looks quite sad, and maybe Jack Ma, yeah, it's just his facial structures suggest that he's angry, but that's not really the case. All right. So that's it for the inference of our model. Next, we will pack our model to ONNX format. Since we want to deploy our models in different environments, or want it to run in different frameworks like PyTorch or TensorFlow, we need to pack our model in a format that is able to meet the requirement. And the format that we choose is ONNX. What is ONNX? ONNX is an open file format to store the trained machine learning models. It can be used to deploy the model in various cloud platforms and various devices. So to export the model to this format, I'm going to write a separate file. So here I create a file, convert model to ONNX, and put it in the root directory. Well, so here we need to have a few imports. Basically, all the imports here are the necessary import to run the inference of the model. Logger here is used to write out the process, and in the main function we will first load the configuration. Again, this type of context manager is used so that we can pass the configuration directly into the main function. So here is the main functions. So we take in the parameter as the configurations, and first we specify the root directory, right? And based on that we get the model path, and then we load the model. Yeah. And we load the data, initialize the data set by setting up the state to fit, and then in order to convert the model to ONNX format, we need to get an input in order to tell the model how the forward pass is run. So input and label can simply be called by taking a batch from the train data loader. Now is the main function. To export the model to ONNX format, we use doc.onnx.export. There are a few key arguments in the export functions. So the first argument is the model, second is input batch, third is the output path to the ONNX model, and offset versions here is 15. The next key argument could be input names, output names, and dynamic access. So here I want to focus on explaining the dynamic access. So other arguments are more or less clear. So the dynamic access argument is used to specify the type of the dimensions that we want to be dynamic. So here, for example, we set the batch size of the input to be dynamic so that this model can run on different batch size. Right? By default, if you don't specify dynamic access, you can only run one image at a time. But by specifying the dynamic access for the batch size, which is a dimension 0, you can run in one pass, for example, 4 image or 8 image. And here the same thing, the output, for the output, the dynamic axis is also the batch size. Yeah, and then we just hit run, or we just run this function in the main function in order to convert the model to the model in ONNX format. Let me open the terminal and run this function. Convert model to ONNX.py. Well, here I already actually converted it, so it's already in my directory. But let's see. So this will be the new one that should override this existing one. But loading data takes some time because we have a large CSV file. Alright, so the conversion is finished, right? And here is the converted model. So next we are going to use this ONNX model to run inference. Well, to do that, on the root directory I create inference ONNX Python script. Basically, the inference with ONNX format is very similar with the inference with the usual model. The big difference is that in order to do inference with a model in ONNX format, we need to set up an ONNX runtime sessions. So in this class, in the init method, besides all the usual thing, which is initiate the emotion and loading the model, we need to set up runtime sessions. So here you can see I initiate the session to be inference sessions on the ONNX model. And in this case, I specify the provider to CPU because I don't have access to GPU. So if you have access to GPU, you can accelerate the inference speed by specifying the provider to GPU execution provider. Well, here I also set up a context timing so that I can time the process. So this timing here is in my utility file. So it is just a decorator in order to time the process. So let's go back to the script here. In the inference image functions, this is the way that I use so that well, basically I create another so-called undecorated version internally to do the inference on the image, and then for the wrapper I will call these functions. So the timing is on the wrapper. So here you can see most of the things are more or less the same as before, and the core here lies in the prediction on a facial regions. So let's go to this function. All right, so here is the main thing. So the prediction function here take in the parameter as a facial regions, and as before, we need to convert this facial region to grayscale, resize to size 48 by 48, sorry, and we apply the chain transform, sorry, the validation transform, which is to crop the image into 10 sub-image of shape 44 by 44 and then stack them. ONNX only accept input as numpy array, so we need to convert this tensor to numpy array, and now we can run inference in ONNX runtime that we set up earlier by doing the following. So well, to run inference with ONNX runtime, first we need to set the input so that it is in the form that we expect, right? For setting the input, we need to have the input in the form of dictionary, where the first term here is a key for the dictionary. In this case, if you look back to the convert functions, we specify the input name as input. So the key here is simply input. Well, where is my script? Okay, here. So this is simply inputs, and then we put in the numpy array. For the output, well, we also need to specify, we call the session, right? First we call the session by self dot sessions, and we run it on the input. But here there are two parameters. The first parameter is actually the name of the output that we wish to have. In our case, we only have output. If you look back again, the convert script here, we specify the output names to be output. So in other case, there can be different outputs, where if you want to get some particular output, you need to specify the name. The usual way to do it is just to specify none. So in this case, all the outputs will be given, right? And I will keep it as none. And now we get this output, and we can get prediction by taking the mean of the prediction on all the 10 sub-image, and then the emotion that we get will be the one with the highest prediction. So this is a prediction on single facial regions. So now using this, the rest would be relatively easy. So inference on image here, we simply extract all the facial locations, loop through every single location, get the prediction, and display the information on the image. Right? For video, we do the same. And for webcam, we more or less do the same. And we use the same technique as before. Resize the frame by 1/4, both the height and the width. Do the inference on the resize frame, and then display the result. Right? Everything is the same. The main function is the same. So here I will skip this. Let's do the inference on webcam, because just now I haven't done it. So let's do the inference in this case, do it on webcam. Okay, let me just copy the code for inference here. For webcam, I need to specify this argument as camera index, and let's just use my laptop webcam. Alright, so you can see it works pretty okay. I wouldn't say excellent, but one emotion I fail to make is angry. I think for angry, usually it's easier if you can show a lot of these, and you also should be minded that under different lighting conditions, the result might be different. So I have experimented this under bad lighting condition, like at night, the result is ugly. So if you have good lighting condition, it could be better. This is the end of this episode. In the next one, we will be packing our ONNX model into a Docker image, which will be used for deployment with Fast API. See you next time.